Okay, let's do our first optoelectronic device for semiconductors. We're going to start with photovoltaics, which are solar cells, and we'll also build in this lecture towards photodiodes, which are used as detectors. The photo to get us started here is just a large array of solar cells on a solar farm. These are appearing all over the U.S., and it's not too surprising that most of them are appearing here out in California and the Southwest, where the sunlight irradiance you can see plotted here, the highest levels being the dark red, where you basically have the most sunlight to generate photovoltaic power. So, a bit of review. Let's say we hit silicon with wavelengths of light less than 1.1 micron, which means the energy of the photon is greater than 1.12 eV, using that 1240 over lambda equation. And we know that one photon will give us one electron hole pair. Okay? And we'll say for this light that's hitting the silicon, we have 10 to the 13th photons per light every 1 microsecond, meaning that our optical generation rate will be 10 to the 13th per cubic centimeter per microsecond. Okay? And then we said previously, if we have a minority carrier lifetime, or just carrier lifetimes, of 5 microseconds, then we can get the excess carrier concentration as the optical generation rate times the lifetime, because these are competing. This is creating carriers, this is making them go away. The balance gives us the concentration. We multiply that out, and we get an excess of 5 times 10 to the 13th per cubic centimeter for both holes and electrons generated. So at this point, we want to do something useful with this. So let's collect the optically generated charge. But how can we do that? Well, not surprising in this course that it's all going to come back to diodes. And so we're going to set up a diode, and we're going to collect that charge using the diode. So let's look at a diode under illumination here, and let's focus our attention over here. So let's assume photons are coming in here. Notice that I have reverse biased the diode, so I have negative potential on the P side. So I've reverse biased a little bit. You can tell because the Fermi levels are offset. And let's ask some key questions you should be able to answer. So, carriers generated out in the bulk of the P in the N, way out here, way out here, way out here, far away from the depletion region edge. Do they do anything? If I have a photon of light come in and it generates an electron, so I have an electron up here, a hole here, is that going to do anything for me? Well, if you think about that, that's no different than having a semiconductor wafer just sitting on a table. It'll just get hot. Basically, light will come in, you'll generate electrons, it'll generate a hole, they'll move around, they'll find each other, and it will recombine, and that recombination will go back to heat. And so way out here in the N-type and the P-type regions, all I'm going to do is basically make this PN junction heat up, which is not generating electrical energy, which is what I'm after. Okay, the next question. Carriers generated inside the depletion region, what will happen for them? So if I have a photon absorbed here, what would happen? So let's say I have a photon absorbed, and it creates an electron, and it creates a hole as a result too. So an electron goes up here, here's my hole. What do I got here? Well, look, I've got E field, right? The electron will go this way, the hole will be swept this way. It's the bubbles, essentially, right? This is the water. And now I've separated that charge. And if I keep bringing in more photons, I'll have more and more charge coming out here. And that charge can then flow through my circuit and generate a current. So now I've got optically generated charge, which I can collect as optical power, optically generated power, or electrical power, that is. Okay, next question. Carriers generated within a diffusion length of the depletion region. So within a diffusion length, so this is meaning that if I generate carriers within a diffusion length here or a diffusion length here, will they do anything? Well, remember, when we had a reverse bias PN junction like this, remember all on the P side that our minority carrier electron concentration went to 0? Meaning that every minority carrier electron that's generated thermally, we said previously, if it's close enough, it's going to fall off the cliff edge. It basically is created thermally, it wiggles around, it falls off the cliff edge. And then way out here, it's too far from the edge to make it there, right? And so that's why we had this profile showing that if you're within a diffusion length of the edge of the depletion region, here's the depletion region, then the electron concentration goes down because these electrons are basically falling off the cliff. Same over here, holes that are thermally generated, electron up here, hole moves around, falls off the cliff edge. So that will be the same effect. If I have electrons created here or holes created here, they will be close enough to the depletion edge that they will also move around, fall off the cliff, and be swept to the other side, and also add to my optically generated current. Question, which matters, majority or minority carriers? Well, if you think about it, all that matters here are the minority carriers. The minority carrier hole is the one that's going to get swept across. An electron generated here, it's just going to sit here, right? And so the ones that basically are swept across are the minority carriers. Minority carrier electrons, because this is p-type material. Minority carrier holes, because this is n-type material. So let's adopt our diode equation. It's not too difficult to do. Okay. So what I want to do is I'm going to take my optically generated current. I'm going to calculate it as Q to give me a coulomb, because I need coulombs per second. Optical generation rate, which is per unit cc per second. And if I multiply that by cubic centimeters, then 1 over cc per second, this is GOP over cc per second, times cubic centimeters will just give me 1 over seconds. 1 over seconds times Q will give me coulombs per seconds, which is current. And so how do I calculate this? Well, we already know how to calculate GOP. That's the number of photons hitting this. Q is the charge of an electron, right? And the volume is the area times the width of this. So the area would be, if this is the diode here, it would be the cross-sectional area in this direction. So what's the cross-sectional area of this? And then this would be the width here, okay? But notice the width also includes my diffusion lengths, LP and LN. So it's basically the cross-sectional area, the width of the depletion region, and within a diffusion length of the depletion region as well, which is, we said, any of the carriers generated within LN or LP or within W will be swept across by the E field. And so that's how I calculate my total width of the optical generated area that contributes to optical current. Now, if I have electrons going this way and holes going this way, holes going this way is current in this direction, right? Electrons in this way is current in this direction. Current in this direction is in the opposite direction for a normally forward bias PN junction, right? You normally put positive voltage on the P side and get current this way. And so the optically generated current is negative. It's going in the opposite direction. It should be negative on the IV plot. So if I come over here to my diode plot, here's current versus voltage. Here's my normal diode equation here. As I increase my light on this reverse bias diode, because I reverse biased it, you could see it's becoming more negative because I have more current going in the opposite direction. And so it's negative. And if I therefore add the optically generated current to my diode equation, here's my diode equation, then I have to subtract it because, again, it is in the opposite direction. I could then take this equation, I will just substitute in all this stuff for IOP, I'll put it in there, and I get a full equation with all the parameters I need to calculate how much current you would get for a diode under illumination. So at this point, let's stop there. Make sure you're absolutely solid on that, and review these questions. We just covered these. Should be very easy to answer. Take a break and then come back to the next part.